Sydney. How are we all doing today? My name's Murad, and I'm an associate professor at UNSW. What I do is I try and take sunlight and turn it into electricity. Now, you may have noticed that Murad is not the most common name. It's actually Arabic. Now the whole audience pulls back because we're expecting a lecture on colonization or racism or a colorblind society. Well, let me put your mind at ease. I do see color, and like all children, I know some colors are better than others. And we need to know that to make good solar cells. But Murad's actually Arabic for hope, and I am actually hopeful. Okay, I'm hopeful that we can beat climate change. I'm hopeful that we can create a more sustainable society, and like every scientist in this room, I'm hopeful I can make more than minimum wage. So, luckily my PhD days are behind me, but if there are a few PhD students in the audience, so please buy them a drink or a hot meal. The second half of that headline is actually correct, though. I do still enjoy instant noodles, but that's just because of what passes as fine dining growing up in Penrith. And being this eclectic mix of identities, I've got an Arabic name, I'm from Penrith, now I'm an academic and a scientist. What that's attracted me to is problems that affect everyone, regardless of your identity. And that's why I'm really attracted to trying to solve the energy crisis. The way we are producing energy today produces CO2 way too fast for Earth's natural systems to deal with. Now, I don't want to be an alarmist, but some of you are ahead of me. But we're going to see more and more images of sad polar bears clinging to ever-melting pieces of ice. And we're going to get more and more wildfires. And finally, as these spread, we're going to have climate refugees. But I'm here to tell you that an inferno of displaced polar bears marching on the Opera House is not necessarily our future, okay? We're working on making solar cells that convert up to 42% of sunlight into electricity. That's way more than the 29% that current commercial cells do. But these are just numbers. So what does this mean for you? Well, ladies and gentlemen, brothers and sisters, I have a dream. I have a dream that one day you will be driving your electric car and you will have my solar panels on top. You will get to work and the sun will have charged your car for you. And I have a dream that the only correspondence you will have from AGL is them paying you. And brothers and sisters, I have a dream that this technology will make you happier. It will make you wealthier. And it will make you insufferable. I have a dream. But brothers and sisters, this dream is only in reach if we judge light by its color and not the content of its character. And that is where my story starts, with color and sunlight. Now the sun is an amazing resource, okay? It's our wireless nuclear fusion reactor. And next time you have a chance, you should really just look at the sun. Not like this, okay? There are smarter ways to do this. Way back in the 1600s, Isaac Newton took sunlight, put it through a prism, and then showed that it was made up of all these different colors. I mean, Isaac Newton was a genius, though. He invented calculus, he explained gravity for the first time, and he even discovered the pride flag. He was also a little bit of a lunatic. So he, when you close your eyes, you can see colors, and what he wanted to work out is whether those colors are the same as the colors that you see from sunlight. So he performed an experiment. Closed one eye, he focused on the colors in that eye, and with the other eye, he looked at the fucking sun. So even geniuses make mistakes. Let's fast forward 300 years, and now we get to quantum physics. And we start to learn that sunlight is made up of particles which we call photons. And each of the colors that Newton saw have different energies depending on their colors. So I've got my violet light here, that's a big, strong, buff photon, and red light, which is a weak little baby. Okay? And it's because of this simple fact that violet light has more energy than red light that I've become a violent extremist. I'm sorry, violet extremist. I'm a violet extremist. I believe in violet power. See, the problem is current solar cells, the way they generate electricity is they absorb a photon and then they generate an electron that goes around your circuit, powers your light bulb, powers your toaster. But it doesn't matter what color of light hits your cell, you still get the same amount of energy. It's a one-to-one process. One bit of blue light in, the same amount of electricity out as one photon of red light. As a violet extremist, I can't stand for this equality of outcome. So I'm going to blow up the status quo using a process called fission. Now, let's first address the elephant in the room. The brown man's not making a nuclear bomb. Don't worry, okay? Fission doesn't have to be nuclear, it doesn't have to be about bombs, it just means to split. And remember, although I have an Arabic name, I'm also from Penrith. So I'm not working on nuclear fission, I work on a process called singlet fission. It is seriously called this, okay? But singlet just means there's one single thing that we're doing fission to. So we're splitting one thing. And in this case, we're going to split the energy of one violet photon into 2 electrons, okay? I've actually been studying singlet fission for 15 years since I started my PhD. And you may ask, well, Murad, how can you study something for 15 years? Well, I've got a 2-part answer. The first part is, that's pretty fucking rude. I'm going to justify my life choices to you. Secondly, singlet fission is useful for solar cells, and I'll talk about that later, but it's also useful for quantum computing, it could be useful for biomedical imaging, and even for fundamental physics, so it's kept me busy for a while. But just talking about the solar cells, we have a team of about 20 researchers. They're working on taking this standard industry silicon solar cell. You can see, as I said before, 1 photon in, 1 electron out. So we have 3 photons in, 3 electrons out. We're going to take that and put a singlet fission layer on top and make this singlet fission solar cell. So we got the same 3 photons in, but we have 4 electrons coming out because we split the energy of that violet photon. The really cool advantage of this is that we get to build on top of a silicon cell, which has been established for over 50 years, all right? So we're building on all of that maturity, and we've already made a prototype. So I'm really excited about this, and I think that it could maybe even be on your houses in the next decade. So you may ask if you have a prototype, why is it still going to take 10 years? Fuck you again. This is really hard, okay? The purple layer there is actually, we're designing molecules to go in there and synthesizing them for the first time, and then we have to deposit them with nanometer precision. So that's 1/10,000th of the width of a human hair. But even though there are technical challenges, we are making really good progress. And I can tell you that a sustainable utopia is in reach if we can just reach for inequality of colors.